Welcome back to Wood Engineering. I'm Jeff Rochko from Carleton University, and in this video, we're going to do one additional bolted connection example, but this time, instead of being given a connection and having to design it, we are going to go through the entire design process from the ground up, including iteration, including consideration of spacing, figuring out how many bolts we need, where we're going to put them, how are we going to lay out the plates, and doing all of the checks. So this is kind of another epic example that should give you an idea of the entire design process of designing these kind of bolted connections by hand. So hopefully it'll be very illuminating for you. And so what we're doing here is we're designing kind of a simple knife plate connection where we have cut a slot in the center of a piece of glue lam. So if this is the end of our piece of glue lam, we cut a slot down the middle so that we can fit a plate in the slot. So even though we don't have actually three members, we only have two members. This is still a three-member connection because at the section here, we have 1, 2, 3 members. Okay, so because of the slot. So where we cut the slot, those two separate pieces on either side of the slot are each considered separate members from the point of view of designing the connection. So we're designing a three-member knife plate connection here. And to give ourselves a target load, we're looking at, for this 20 FEX Doug Fir glue lam beam, which is 265 by 608, which we're given. We're going to design a connection that's going to be able to resist 50% of the total tension resistance of this beam. Okay, you know, not including the net area reduction. Or maybe I did include it, I don't remember. So, you know, keep in mind by the time we get to the end, we haven't designed this connection, and you'll see the connection is going to be pretty sizable. That connection is only going to be able to resist 50% of the total tension resistance of this member. So, you know, keep in mind that when we design wood beams, wood members, especially wood elements in tension, often it's the connection that is the limiting strength of the entire member. Okay, so I've given details about the steel plate in terms of thickness. So it's 6 millimeters thick. We are going to figure out how big the plate should be, not from the point of view of steel design, just from the point of view of geometry. You're going to see that we're going to consider shrinkage in this connection, so that will have some impact on how we design our steel plate. We're given the grade is A306, so that's fine. So we have a 6 millimeter thick plate, so that also defines the width of our slot in the end of the glue lam beam. And we are given a grade of bolt only. So we're saying we're using A307 bolts, which is the kind of default kind of bolt described in the standard. And we're going to figure out how many of those bolts we're going to use. Now, in contrast to basically all of the previous examples that I've done in this entire course in video, I'm not going to write everything out for this example. I've done it all in MathCAD, and I'm going to highlight some things, and I'm going to discuss through this example just to save my own, you know, carpal tunnel. All right, so let's get started. We're going to have to do a lot of considerations, and you'll notice that half of this example is just figuring out how many bolts we should use and what size of bolts we should use. And that is going to be very interesting. Okay, so we're doing dry conditions and standard term loads. So KD equals 1, and yeah, we're assuming that the steel plate is adequate. So KD is 1, KST equals 1, KSV, KSF, KT, KH, these are all 1 because we're doing standard dry conditions. Okay. So first of all, we're said here that we're going to design for 50% of the gross tensile resistance. So as I mentioned, we're going to do a calculation to figure out what that gross tensile resistance is, which gives us our target force. In practice, I mean, I could have just given the force here. This is an extra step. The force is going to come from our structural analysis, obviously, of what kind of force we need to put on this connection. So, but we're just going to design it right now for 50% of the gross tensile resistance as an exercise. So, you know, I'm going to go through these checks a little bit more quickly than I have in the past since we've done them all before in order to save time in the video. So we're just doing a regular tension resistance check here. We're getting our FTN and FTG, but obviously we're going to focus on the FTG because we're looking at the gross section, as I mentioned. So all these values come from the table 7.3, or it's 7.2 if you're talking about 08619. And I've calculated my gross area here so I can do the gross tensile resistance check. Okay, so we do our capital FTG, which takes into account the modification factors, which are all 1 in this case. And then we calculate our TR phi T FTG times AG, and we get 2,219 kilonewtons. So this is a very big piece of wood. If I was able to adequately hold this piece of wood for its full tension resistance, it would be able to resist 2 meganewtons of force in tension. So, you know, wood is very strong in tension. We've gone over this before. But again, typically we're going to be limited by connection design because it's tough to design adequate connections in wood. Okay, so that gives us our target, which we mentioned is going to be 50% of that maximum gross area TR. And so our target force is going to be 1109 kilonewtons. So this is what we're going to be targeting for all of our different load checks. So for this particular element, right, we're doing a bolted connection, so we're going to check yielding. And then all of the load in this connection is parallel to grain. So we're not going to have to check splitting. We're not going to have to check the parallel perpendicular interaction. So we're only going to be looking at row shear, group tear out, and net tension, plus, again, the yielding. So, but believe me, it's going to be enough. We're going to see. Okay. So we have now our target connection load. So we're good to go in terms of figuring out our design. Okay, so we have a really big design space right now. We don't know how many bolts. We don't know what size of bolts we're going to use. We don't know the size of the connection. We don't know how many bolts we can fit on the piece. So first step that I would do here is come up with some spacings for a few different bolt requirements so that we can explore what kind of bolts we can use here. So I'm saying, you know, that there's a big connection, so probably we're not going to use 1/2-inch bolts. Those will look quite undersized here, especially because the length of these bolts is going to have to be at least 265 millimeters, which is, you know, almost a foot long. So we're going to probably have to use fairly big bolts. I have put 3/4-inch bolts or 1-inch bolts. And so we're going to explore both of those possibilities and see what we get. Okay, so we are going to do this step after checking the bolt design tables. And I'm going to show you the bolt design tables in the wood design manual and explain a bit how they work so that we can come up with some estimates of the number of bolts that we're going to need. And that's going to be very useful in our design process, because otherwise, how do we even figure out how many bolts that we need without having design tables? So you're going to want to make use of those design tables. Okay, so let's look first at the spacing requirements. Let me remind you exactly what the requirements are. Okay, so you will recall that we have bolt spacing requirements here. Okay, so this is what we looked at when we did our design of bolted connections. All right, so we have a spacing within a row. So this is for load parallel to grain, which is our circumstance. We have a spacing parallel to the grain or within the row, depending on whether you're talking about OD6, 14, and 19. These requirements are the same. It's just presented a little bit different in both. And we have, so these are our rows. The rows are parallel to the grain, if you recall. And then we have our spacing perpendicular to grain, which is 3DF, which is also the spacing between rows, that's called. And then we have our unloaded edge distance here on both sides, which is a maximum of 1.5 DF, or half of the between row spacing or perpendicular to grain row spacing. And then we have our end distance, which in this case is a loaded end distance, because the bolts in the beam, right? In the beam, the bolts want to pull out the end, right? Because we have this load on one side pulling on the wood beam, and the bolts are pulling opposite to that. So they're pulling towards the end. So that makes this end here a loaded end. So we are talking then about a loaded end distance AL, which is a maximum of 5 DF or 50 millimeters. So I am going to find all of these requirements for both 3/4-inch bolts and 1-inch bolts. You know, they're going to change because these requirements are mostly dependent on DF, the diameter of the fastener. so let's go back. Okay, so here I find all of those requirements for both. Here's for 3/4 inch bolts and 1 inch bolts. This is the bolt diameter here of each. 19.05 is 3/4 inch, 25.4 is 1 inch. And then these are all of those requirements that we were just looking at. Okay, so now I know my row spacing has to be, so this is the spacing between rows, has to be at least 57 millimeters for 3/4 inch bolts, and it has to be at least 76 millimeters for 1 inch bolts, right? Unloaded edge distance, at least 1.5 times DF1. Okay, we're going to check these in detail later, so I'm just kind of checking them for now. Okay, so then loaded end distance, right? 5 times DF, and within row spacing, 4 times DF. So these give me all of my requirements for geometrically laying out all my bolts in my piece. Okay, so now based on the between row spacing and the edge distances, okay, so I know now my edge distance here, my unloaded edge distance, I know how much space I need to leave in between rows. Now I can figure out how many rows total I can fit on my member because I know the depth of my member. So that will be different for 3/4 inch bolts versus for 1 inch bolts. So for the 3/4 inch bolts, available depth for rows is my D. So I'm looking at basically, here's my member. I've got all these rows of bolts, right? However many I have. I have my total depth here is D. And then I have here EP and here EP. And so this is my total depth available here, D avail. Okay, which is the total like space that I can fit bolts in. And so I get D minus 2 times the edge distance EP. And so I get 550.8 because my D was 608. So 608 minus the edge spacing gives me available rows for bolts. So if I know that available length, then I can divide by the row spacing, the minimum row spacing here, 57.2, which is what I got up here. And then I add 1. Why? Because let me see if I have a situation like this and I have, let me say 4 here. I find this, I divide it by the row spacing, and you'll see that I have 3 row spacings for 4 bolt rows. Okay, so that's what the +1 is. Because I've calculated basically how many spaces that I have. That's my D available divided by the row spacing. And then I add 1 because I have 4 rows for 3 spaces. So then I get that I can fit basically 10.629 rows of bolts if they're 3/4 inch. Okay, so it's a little bit different than what I showed here. You know, this was just a very rough drawing of geometry. And, you know, I've drawn it kind of like, oh, it looks like it's going to fit 2 or 3 rows of bolts. But actually, if I look at it at true scale, then I find that I can actually fit about 10 rows of bolts on there. So this SC would be called SQ in 086-19. That's what this number is here. Okay. So let's not forget that we need to satisfy this net area requirement. Okay, so remember that our net area has to be at least 75% of our gross area. So this is another limit on the number of rows of bolts that we can have. Because as we cut bolts out, you know, as we cut these bolts, we are removing area from the net section here. So I can only remove so many bolt areas before I get to that 75% limit. Okay, so let's find our net area. So the first thing that we need to do when we're looking at net area is we have to remove the area of the slot. So we take out this area here. Okay, so area of the slot equals AG, which is our total net area, our total gross area, minus 6 millimeters, which is the thickness of the slot, times D, which is the depth of the slot. And I get 157,472 millimeters squared. So that is, that's basically the area of this side and this side together. Then I can remove a bolt. Okay, so the area of a bolt that I'm going to remove is the diameter of the fastener. So this is the size of the hole, remember, is the diameter of the fastener, which in this case is 19.05 millimeters, plus 2 millimeters to account for the hole being bigger than the fastener. So for a 3/4 inch bolt, I have a 21.05 millimeter hole. So then to remove that hole, I have to remove area like this, not taking into account the area that I already removed from the slot. So I basically have the diameter of the hole multiplied by B, this is B, the width of the member, minus 6 millimeters to account for the fact that I already removed the area of the slot. And so each bolt removes 52 millimeters squared from the total net area. Okay, so now I can figure out how many bolts I can remove before I get to that 75% net area reduction maximum. Sorry, it's 25% reduction to give us 75% of the gross area. Okay, so then I say I am having basically this numerator here. Now, you know, like I've laid these out in equations because I have to, according to, you know, because I'm using MathCAD here. So I'm actually writing out the equations explicitly. But I mean, obviously, if you're doing this, you know, I'm sure you can figure this out just by kind of thinking about it logically. But this gives it a bit more explicitly the step-by-step, right? Because this is the amount of net area that I have when I remove n bolts, right? So I start with n net slot, which is these two red arrows here, right? The total size on either side of the slot, minus the area of one bolt hole taken out, times the number of rows of bolts that I have, right? Which is basically the number of bolts that I have at the net section. So when I do remove that, so I can rearrange this equation basically and solve for the number of rows, and I get 6.719 rows. So that's how many rows of bolts I can have before I get below 0.75 AG in taking out net area. So up here, I could fit 10 rows according to the geometry, but according to net area, I can only fit actually 6 rows of bolts. Okay, so I have to consider both of these requirements basically. Okay, so now that we have that, we can move on to figure out how many bolt rows we can fit for 1-inch bolts. So you can see how much work we're putting in here just figuring out the geometry. Okay, so this is the exact same process for 1-inch bolts, so I think we don't have to go in so much detail. The available depth is a little bit less because my EP, my edge distance on either side, is a little bit greater now because the bolts are a bit bigger. So the maximum number of rows that I can fit, you know, including the fact that the spacing between the rows now is bigger as well because the bolts are bigger, is 7 rows. Almost 8. You could probably say 8. But anyway, 7 rows max. Now, if we take into the net area reduction again, now, of course, for each row of bolts, I'm going to have a bigger hole for the bolt because the bolt is bigger. So I take that bolt, add 2 millimeters, and I get approximate size of the hole. And then if I solve that equation again to figure out how many rows I can introduce without getting below 75% of the gross area, then I get actually 5 rows of bolts. Okay, so now, you know, we've come up with some really good information about limiting our design. Okay, so this is a good approach to take. Like I start with basically infinite possibilities in my design, and using all of the requirements that I know exist, I'm going to narrow down my design space into some actual good possibilities. So right now I know that for 3/4 inch bolts, I can use 6 rows maximum, so I know I have a max. And for 1-inch bolts, I can use 5, so 1 fewer rows of bolts. Okay, so now we can kind of go to the tables and figure out how many bolts we would need total. Okay, so we know that we have 6 rows of bolts or 5 rows of bolts, depending on the size of the bolt. And if we go to the tables, then we can figure out basically what the strength of our rows of bolts will be, so that we can figure out how many bolts we need in each row in order to satisfy our overall strength requirement. And you'll recall that our overall strength requirement was 1109 kilonewtons, which was 50% of the total strength of the member. So let's go to those tables. So I'm going to the Wood Design Manual in the first volume. So here are the bolt selection tables. This is where they start. There are notes on page 408, which have some additional information here that says basically how you can calculate the actual strength of these. So don't forget to look at the notes. We'll talk about that in a second. And we have all sorts of different types of connections as well. So you can see that before these tables, it lays out basically, here are all the different types of connections that are covered by these design tables. Okay, so we need to figure out our type first. Okay, so it's not any of these. We know we have a steel knife plate connection. So we're looking at double shear, not steel side plates. We're looking at double shear steel internal plates in parallel to grain loading. So this is type 11. So we're looking at this one right here. This is what our situation looks like. So this is type 11. So we need a table that will give us type 11 strengths. So you can see here, if I go to the first one, I've got basically, it's a bit hard to see. I got type 1, type 2, type 3. This is single shear wood side plate. You know, it tells you at the top as well what kind of designs these tables are for. So we're looking for double shear with a steel internal plate, not steel side plate, steel internal plate. Here we go. And you can see here that we have type 11, parallel to grain resistance, double shear 6mm steel internal plate. Well, isn't that convenient that we actually are using a 6mm plate in this example? Okay, so it's going to give us basically row shear capacity and group tear out capacity for different sizes of bolts. So here you can see there's for a 1/2 inch bolt, here's for a 5/8. So we haven't included 5/8 in our consideration. So we've got basically 3/4 and 1. So I have to go a little bit further. Yeah, so here's the ones for 3/4 and 7/8. And then we should have, again, 1 inch bolt numbers here. Okay, so now let's think about how we're going to use this table. So let's go to the 3/4 inch. Okay, so here's where a 3/4 inch starts. So you see we're going to get row shear and group tear out strengths. And we need to figure this out for Douglas fir, because that is our species, right? So you remember that we have, let's remember our connection geometry. So we have Douglas fir larch glulam, 24 FEX. And what is our side plate thickness here? It's going to be this thickness here, which is 265 minus 6, which is the slot, divided by 2. So if I go down to where I'm choosing these here, you'll see that I've taken that into account. Side member thickness is then, right, this is my total thickness of the member minus 6 for the slot divided by 2. So my side member thickness is about 130. So that's what I'm looking for in the tables. So if I go to my tables now again, okay, you'll see we have 3/4 inch bolts. We've got basically 140 here. And phew, close call. I'm looking at the wrong table. And why is that? Because on top of this being double shear 6mm steel internal plate, 3/4 inch bolt or dowel for type 11, which is our situation, parallel to grain resistance, okay, 3/4 inch type 11, double shear 6mm steel internal side plate. Over here, where it has species, you see I said Doug fir larch. This is another thing you have to look for. Species here is for sawn lumber. So this is the sawn lumber table. So I got to go a little bit further, actually. And now I get, here are the ones for glulam. See, there's glulam. Okay, so I'm going to the next table here. So wondering why these numbers weren't making sense. Okay, so here we go. 3/4 inch bolt or dowel, double shear, 6mm steel internal side plate, type 11 parallel to grain resistance for glulam, Douglas fir larch. And our side plate thickness is 130. Okay, if it wasn't exactly this number, then I can try to figure out what my strength would be by interpolating between these numbers. Okay, so you see I have Douglas fir larch, 130mm side plate thickness. That's my wood member thickness in this case on either side of the knife plate. And you can see that I have spacing parallel to grain. What's my row shear? What's my group tear out? It depends. You see I have 2 rows here because it's giving me 2 different options. So obviously my row shear strength is going to depend on how long my rows are, right? Because row shear is based on the spacing between the bolts. So it gives me 2 different options for spacing. One of these is the minimum spacing, 76, right? Which is based on the 4DF requirement for a 3/4 inch bolt, okay? And one here is greater than 120. Why is there a greater than 120 value? Because as my row shear increases, eventually my failure mechanism is going to switch from row shear to yielding. So if I do anything greater than 120, then the row shear is not going to govern. So this gives me basically what would be the row shear strength in that case. Okay, so that's why I have 2 options here. So basically in my tables, I'm going to look at both of these cases and see what would the situation be if I use the minimum spacing, and what would the situation be if I pick this kind of maximum effective spacing. If I go any greater than this, I don't get any benefit for strength. So that's why they're saying greater than 120mm spacing parallel to grain, because I'm going to switch failure modes, as I mentioned. Okay, so here we have capacity per bolt or dowel in 1 row. So I have, you know, a row of bolts, 1, 2, 3, 4 bolts. Then my row shear for that row is going to be 4 times this number. Okay, so I have 21.6 for the minimum and 34.1 for the greater than 120, which is what I'm putting in my table down here. So I'm just, right now, I'm just recording these numbers down here. Okay, so for 3/4 inch bolts, my row shear capacity is 21.6 and 34.1, depending on my row spacing. Then I'm also going to pick out the values for my group tear out. Okay, so if I go to the next column here, it gives me group tear out resistance. Of course, these numbers are assuming standard load duration, no service condition factors or anything like that. Okay, and I get 57 and 114 as 2 options for group width. Okay, so this is the area of the tension part of the group tear out. Okay, so depending on what that is, then it gives me a certain tension resistance. So this only gives me the tension resistance part of the group tear out. Why? Because I can combine this with the row shear resistance to get the total group tear out resistance. Because remember that when I calculate group tear out, I have one portion that's coming from the rows failing and one portion that's coming from the tension leg basically failing. Okay, so that gives me the tension resistance of 134 or 268, depending on how wide the group is, obviously, because the width of the group will change the area of the net tension face. Okay, so I'm going to record those values as well down here. So this is just the tension plane strength. Okay, 134 and 268, those are the values from my table. I'm going to do the same thing for a 1-inch bolt. So I'm going to go to this next table here and do the same thing for Doug fir 130, get these 2 values, get this value for the group width for 1-inch bolt. There's only one potential value there that they're giving in the table of 76mm group width. And I'm recording those values as well down here for 1-inch bolts. Okay, so now I have some numbers that I can use to calculate basically what is the resistance of different situations, like if I have different numbers of bolts. And there are some equations here for calculating what those resistance will be based on the values that I get in the table. You'll notice that this PRF, this is not a variable that we've seen before, PRF. That's not in the standard. That's because this is like an effective row shear that we're going to plug into another equation to get our PRRT, which is actually a value that we have in the standard, right? PRRT is a design resistance. It's the resistance of all the rows. So if I go back to the standard, you know, how do I use these PRF values and this GRT value, which are not values that are given in the standard? I go to the bottom of the table. So this is basically the last page in the table for double shear. Actually, both of these have it. I go to the bottom of the table and you see notes. Okay, so the notes are very useful. Okay, it says, it tells you spacing parallel to grain is the lesser of the loaded end distance and the spacing between bolts in a row. So that's something we already know. Group width is center to center spacing of the outermost rows of bolts. So that's something we already know. We know side member thickness already. Okay, the tabulated values of GRT are based on the assumption that there are a maximum number of rows of bolts or dowels allowed within the group width with the row spacing equal to 3df. So that's saying, you know, if my group width was 76 and I could fit, you know, only two rows of bolts there, it's assuming that there are two. Why? Because that judges how many holes you have to take out in order to calculate the GRRT. Okay, so for type 11 connections in members loaded in compression, the connection capacity is this. Okay, and why? Because for compression, it's only the row shear strength. Okay, so they give basically a value here for strength, PRRT, which is our strength from the standard, the lesser of PRF, which is the value from the table, times NC, number of bolts in a row, times number of rows, times KD, times KS, times KT. Those are our modification factors. Okay, and then, or NU prime times NC times NR times KDY, KSF, KT. So that's a yielding strength that I'm going to get from another table. I'm going to leave that off for now. For now, in my preliminary design, I'm just assuming that yielding is not going to govern. For type 11 connections loaded in tension, we have those same requirements plus group tear out. So remember that group tear out is only applicable to members loaded in tension because I need to tear the chunk out of the piece of wood out the end. So it doesn't apply in compression. So for that, you see I have PRF, which is my row shear, times NC. So basically this is the value of one row shear. And remember that makes sense because one row shear has two shear planes. So we basically separate those two shear planes to either side of the group. Times NC, which is the number of bolts in a row, plus this GRT value that we get from the table, times a JTR value from table 7.9, which we'll look at in a second, times KD, KS, TKT. Okay, so what's JTR? For that, I have to go over here for page 452, tension factor for group tear out resistance. Okay, so depending on species here, I have a different factor. Okay, so this is taking into account kind of size effect and all those things that are not taken into account in that particular value. You know, like the strengths are different between different grades and stuff. Actually, this is a grid, so it has nothing to do with size effects, right? It has to do with grade. Okay, so for glulam, we don't have variable grades like that in the same way, so it's not going to affect the strength of the connection very much because the FV for all the glulam values is more or less the same, except here for 18TE. So since we have Douglas fir larch 24FEX, our JTR value is going to be 1.0. So this is how basically they apply those tables to all of the different grades and yeah, basically all the different species and grades of lumber, because you know that all the values for strength are so different between all those. But for our glulam case, the 24FEX is going to be 1.0. Okay, so going back to our design here. So here I'm just laying out basically what those strengths are. Those are the equations from the tables that we just looked at. All our K factors happen to be 1. And as we just saw, our JTR for glulam 24FEX equals 1. Okay, so now that we know these PRRF values and the GRT values, we can easily apply these equations to give us the total strength of a connection for different scenarios. So I'm going to look at some different scenarios so that we can try to choose one that would be the best for our case. Okay, so we're doing maximum number of rows. So we're assuming that we're going to use the maximum number of rows possible so that our connection is as efficient as possible. We're going to use a minimum row spacing. And we're going to try to calculate how many bolts we need. Now, we're not necessarily going to use that minimum row spacing in our final design, but for now, this is a good assumption. So, okay, so let's say first scenario, we're going to use 3/4 inch bolts, and we're going to space them at 76 millimeters within the row. So that's as close as we can space them. So we're making our bolts as compact as possible. Okay, because 76 is our minimum within row spacing. That's the minimum parallel to grain row spacing for 3/4 inch bolts. Okay, so this was our target. So now we can calculate how many bolts do we need total. Okay, so based on row shear, we had, so basically we're rearranging this equation up here. We're solving for NC, which is the number of bolts within a row. Because we already know the number of rows, we're saying that we're going to use the maximum number of rows, which is 6 for our 3/4 inch bolts. And we're taking our PRF from the table, and all these are equal to 1 in this case. So we just get NC is basically PRRT, which is our target strength, divided by PRF, which is the value of the table, divided by 6. And that's what we get here. NC. NF is substituting in for PRRT, because that's our total target strength, divided by the number from the table, divided by 6, because that's our number of rows. And we get 8.56. So we need 9 bolts per row. Now, I rounded up here instead of rounding down, but before, when I was figuring out how many bolts we needed per row, like for example here, we said, okay, how many rows can we fit? And I said we need 6.719 rows can fit. Okay, so can I round up to 7 there? No, because if I go to 7, I have too many rows, and now my spacing requirement won't work. So I had to round down to 6. Here, it's the other way because I'm talking about required strength. Okay, so here, when I solve this equation, I say, okay, we need 8.56 bolts per row in order to satisfy our strength requirement. Okay, so we need 8.56. So can I round down to 8? No, because each bolt that I add adds strength. So if I remove half a bolt and go down to 8, my strength is not going to satisfy that 1109 requirement anymore. So I need to round up. I need that many bolts or more. So I need 9 bolts per row. Okay, let's do the same check for group tear out. Okay, so for group tear out, I'm basically solving this second equation here. Okay, and I'm solving it basically straight out. I'm taking my PRF, I'm multiplying by 9 basically. So I'm saying, okay, let's say given the number of, using 9 bolts per row, does the group tear out get satisfied? And then plus 5. Because I have 5 spaces between the rows, right, times the value from the table. So this value from the table here was for a 114 millimeter group width. So this gives me 1534 total. Okay, so I'm basically here assuming that the rows are spaced out at least 115 apart from each other, times 5. And I'm not sure that that's a good assumption, and we might see that come back. Okay, but anyway, we get something that's way bigger than what our requirement is for NF. So group tear out is satisfied for now. We're going to check these in more detail later. Okay, total number of bolts and connection length, assuming minimum end distance and 9 bolts per row. So now I'm saying, okay, now I've said, okay, I need 6 rows and I have 9 bolts per row according to my row shear strength requirement. So how many bolts do I need total, and what is the length of the connection? Like, I'm trying to say, like, what's the size of my connection? Because I'm going to use these two numbers as a basis for comparison when I look at the other situations. Okay, so I have 54 bolts, 6 times 9, and the length is going to be 95.3. This is what I'm assuming is my loaded end distance, because that's the minimum loaded end distance, times 8 spaces between 9 bolts in the row, times 76, which is the within row spacing, and I get a total length of my connection of 703 millimeters. So to recap, for 3/4 inch bolts, and I have this big glulam beam, and I'm putting the bolts through the connection, and I am getting basically a 700 millimeter long connection. So it's a very big connection. And with that connection, 700 millimeters long, I'm only taking half of the total possible strength of that beam. Because remember, this target of 1109 was only 50% of the gross strength of the beam. So you can see how the connection is limiting the strength of this. Now, you might ask as well at this point, you know, we have two members, one on either side. Well, the values in the table take that into account already. When we do our calculation and we look at member 1 on one side of the knife plate and member 2 on the other, we're going to have to add those together to get the same result. Okay, so let's try a different trial. But before we do that, just give me a second. I'm going to get some water and I'll be right back. Okay, so continuing on, let's try a different situation. So here we were doing 3/4 inch bolts spaced 76 apart from each other within the row. Now let's assume that we're using a larger spacing, because that's going to increase our row shear strength. So maybe we don't need so many bolts. Okay, if row shear governs and I increase the space between the bolts, then as long as yielding is not governing my strength, then I will be basically able to use less bolts potentially. Okay, so we have 3/4 inch bolts spaced at 120. 120 was the maximum value from that table. Okay, so I do the same process. I calculate based on what is my target strength. I divide by the value from the table. That was a per bolt in the row value. I divide by 6 because I have 6 rows, and I need 5.422. So therefore I need 6 bolts per row if I use a larger spacing. Okay, and then I check my tear out resistance the same way as before, assuming that I have a 115 group width for each, between each row basically, and then I satisfy that requirement, so that's okay. And so now if I compare again, I'm going to get 6 times 6 because I have 6 rows, 6 bolts per row. Now I have to use only 36 bolts to meet the same strength requirement. And the length of my connection actually is a little bit less than it was before, 695. So before I needed 54 bolts and I had a length of 703. Now I need only 36 bolts and my length is basically exactly the same as it was before. Okay, so that's interesting. You know, this is something valuable, because if I went with the other design, I'm using more bolts and I'm not increasing my strength at all, really. Okay, so I can use fewer bolts this way. All right, so that's good. Fewer bolts, same size connection, win-win. Okay, so now let's look at the 1-inch bolts. We're doing the exact same process again, so I won't go into terrible detail here. So basically what we get is based on row shear, and we're assuming 5 rows now because we calculated based on spacing requirements that was the maximum number of rows that we could fit for net area. We're going to get, basically, we need 8 bolts per row to satisfy row shear. But then when we check group tear out, we find that we don't actually satisfy the criteria anymore, because group tear out for 8 bolts per row of 5 rows gives us only 954 kilonewtons. So now group tear out is governing. Okay, but this value here, the 181, assumes from the table this value here, 181, assumes that my group width is only 76 millimeters. And I'm saying, well, you know, in our design, the group width is going to be greater than 76 millimeters. So, if I actually do the full calculation here, instead of doing this approximate calculation, then I'll probably be okay for group tear out. And I'm going to do that calculation later. Remember, this step here is all just approximate calculations to figure out potential designs that I can then go through and check all together. Okay, so now the total number, so let's say we'll go forward with this anyway because it's pretty close, and if I increase the spacing between the rows, then we'll probably be fine, which we can do. Then we are going to get basically 5 times 8 is 40 bolts, so just a few more than when we had the 33/4 inch. And my length of my connection is going to be 841. So I use the bigger bolt, I have more bolts required, and my connection is longer. So this is basically a worse design in all categories. Okay, so probably no reason to go with this one. Okay, then the last one is 1-inch bolts spaced further apart, greater than the maximum, greater than that minimum, so that yielding should govern. And if I do that, assuming 5 rows, I only need 5 bolts per row. Okay, so that's pretty good. That's a pretty low number of bolts. And when I check group tear out, I get the same problem again, but again, we're saying, okay, my actual group width, the length of the net tension plane is going to be actually greater in our design than what's assumed in the tables. So let's continue for now. And so that means that for this design, we have 25 bolts total, 5 bolts per row over 5 rows, and my total length is 843. Okay, so now compared to the 3/4 inch with the large spacing, which had 36, this one has fewer bolts per row, but the connection is longer. And I'm using bigger bolts. So now I can kind of figure out, you know, which design do I want to continue with in this analysis. Okay, so, you know, here I'm saying, you know, if I want to minimize the number of bolts, I can go with the 1-inch bolts. Okay, but if I want to minimize the size of the connection, then I should go with the 3/4 inch bolts because it's going to be about 6 inches shorter. So I think I'm going to go that way because, you know, as we discussed, it's often good in timber to use the smaller bolts because we get more yielding. It's a bit more efficient, which we're seeing here. So we're going to use 36 bolts, and there's no reason to go with trial 1 because it's the same size connection and many more bolts, which we already discussed. Okay, but, okay, you might be thinking at this point, okay, so we're going to have basically 36 bolts. We're going to have a 6x6 like big group of bolts. What about shrinkage? Like, isn't this going to be a problem? We talked about shrinkage way at the beginning of the course. And one of the things we talked about is not having big matrices of bolts, right? So I'm going to have to think about this when I detail my connection, and you see that we're going to do that. Okay. So now that we have a better understanding of what kind of design we're going to use, which is this 3/4 inch bolts, 6 rows, 6 bolts per row, I can revisit my spacing requirements and actually kind of come up with an actual spacing that I'm going to use. You know, because look here, for example, row spacing, this is called SQ in 08619 and SC in 08614, is 3DF. So 3DF is 57.15. Am I going to design a connection that has a spacing, a row spacing between rows, basically, of 57.2 millimeters? No, I'm going to use something of a whole number. So I'm going to say, okay, let's start by using a value of 60. So we're going to use 60 for our row spacing. Okay. Since we want to minimize potential for shrinkage, which is what we were just talking about, we want these rows to be as close together as possible so that we don't have a large perpendicular to grain length over which the wood is going to shrink in that connection. So we're going to try to use the minimum here. That is going to have an effect on our group tear out that we're going to see in a minute. Okay, so then unloaded edge distance. We can basically see what our unloaded edge distance will be. Could be, okay, so with 10 rows, remaining available unloaded edge distance. These are the requirements from the standard. So it has to be greater than 1.5 DF or 30, which is half of SC, which we just calculated up here. Okay, so we'll say, okay, we'll just use 30. Okay, so that's a whole, like a round number. We're going to use 30 for the unloaded edge distance. Now, spacing within a row, we already determined that we were going to use 120. That was what we assumed when we looked at the table. The table said greater than 120. This is the value of the row shear per bolt. So we're going to stick with that 120. We can make it a bit bigger if we want, but let's keep it like that for now. That gives us the minimum length of the connection. That's obviously greater than our requirement. So this is just saying this was the requirement and our row spacing is okay. Then our loaded edge distance has to be greater than 5df or 50. And so we're going to say fine. Okay, so, you know, as long as it's greater than 95, we're okay. But remember that when we calculate row shear resistance, the ACRI value, which is the critical length between bolts that we use in the equation, is a minimum of the within row spacing and the loaded edge distance. So if I pick a loaded edge distance that's less than the row spacing, then I have to use the loaded edge distance, that lower value, and assume that it is also the value between all the bolts. So that will just have a big negative impact on my strength. So there's no point setting an AL that's any less than my SR. This is SP if we're talking about 08619, this SR. Okay, so AL should be at least, it should be basically at least SR. There's no point making it any less because I'll get a huge penalty on my strength. Okay, so I'm going to set AL basically equal to SR for now. There's no point making it really any bigger either because a bigger AL will not result in any increase in strength because then SR is the value I'm going to use for ACRI, SP here. Okay, so with all of those requirements, I'm doing a revised drawing. Okay, so this is the first drawing that looks halfway reasonable. All right, so then I have 6 rows of bolts, 1, 2, 3, 4, 5, 6. Okay, and I have spaced them out in a particular way. And what I've done here is instead of putting them all together in a big 6x6 matrix, I've used those spacing requirements that I just calculated. And I spaced them all out into 2 separate plates. Okay, why 2 separate plates? Because now my distance for shrinkage is only going to be this, okay? Assuming that these plates can move relative to each other up and down. If I made this one single plate, then my shrinkage would be happening over this distance, which is much worse. I mean, I could collapse these 3 together into the middle, which would make it a little bit better, but I'm going to have a lot more shrinkage, which could result in cracking in the connection if I use a big set of bolts on a single steel plate. So the way that I'm trying to minimize this problem is using just 3 rows on the top and 3 rows on the bottom with 2 separated knife plates. Okay, you can see here's my spacing between rows, which I'm using as 60 up here, right? And then here is my unloaded edge distance. I have made this a bit bigger than the minimum, which was 30, just so that it doesn't look funny. Okay, so I've used basically my edge distance as being the same as my row spacing. And you can see this 120 and 120, which are my AL. And here is my SR or SP. Okay, and then I put 120 on the end here too, just so that the geometry looked reasonable. That could have probably been less. I mean, those things are going to depend on the design of the steel plate, which, as I mentioned, we're not doing. Okay, so now that we have a better, actually laid out design with actual geometry, now I can go back and calculate actually all of the row shear, group tear out, net tension, and yielding. Okay, so let's talk about the shrinkage in a little bit more detail first. Okay, so that we can see that this shrinkage is reasonable. Okay, so I'm using this 2-plate detail to reduce the potential for shrinkage cracks, as I just said. Let's use our shrinkage calculation to figure out what is the anticipated shrinkage that we're going to get in this connection. Okay, so remember this equation that we talked about way back. S is our shrinkage, equals D, the dimension that we're talking about. MI to MF is our change in moisture content. C is our shrinkage coefficient. So I'm going to make just some assumptions of a range of values here. Now, first of all, D we know. So D is the distance between the farthest bolts, right? So that's this distance here, which is 2 times 60, which is 120. So that's the value that we're using here. Okay. We want to see what is the shrinkage of the wood between those bolts. Okay. We're going to, I'm just making some assumptions. I'm just trying to see, like, is this reasonable or not? Okay, because none of these things is like an exact science, because, you know, we might not know exactly what the moisture content change is. So I'm assuming here that we're going to go somewhere between 15 and 5% moisture content in service. So maybe it comes to site at 15. That's kind of the requirement for wood to come to site. And then let's say during service, this is an interior connection and it's going to get dry in the building and it'll go down to about 5% moisture content over that time. Okay, RC is 0.002 because we're talking about perpendicular to grain shrinkage, which is the one that we're most worried about. In fact, I'm not even worried about the longitudinal shrinkage in this case, even though our connection is pretty long, because it's an order of magnitude lower than this, as we've discussed, 0.0005, if you recall. And if we do that calculation, then I'm going to get a shrinkage of 2.4 millimeters. Okay, that's not too bad. So it's going to shrink 2.4 millimeters over that range of moisture change. That's about the size of the gap around the bolts, right? So our bolts, remember, are 2 millimeters bigger. So it's probably okay. It might, it's still possible that there's going to be some problem. I mean, you know, here it's saying like, we could have some potential issue maybe, but, you know, as I say in the note down there, glulam is a bit more dimensionally stable than lumber. So we're a bit less concerned about the shrinkage for glulam, although we still do need to be concerned, certainly. Okay, so we want to make sure that, you know, given this assumption, we're going to want to make sure that we don't have shrinkage problem, or that we're not having the connection put together at a really high moisture content. Okay. Also, glulam, this member is really big, so it takes a long time for the equilibrium moisture content to be reached through the entire depth of the member. So that's another reason why it's a bit more dimensionally stable than, you know, for example, a smaller piece of lumber. Okay, just for sake of argument, you know, if we had a single plate with the 6 rows of bolts, even if I collapsed all those rows together so that I made them all right next to each other, then what would my shrinkage be? Using that assumption, we would be at around 6 millimeters. And, you know, that's maybe more likely to cause a problem. So I think I'm justified in splitting this up to make it a lot less likely that I'm going to have some kind of shrinkage problem later in my connection. You know, if I wanted to be real on the safe side here, I could have done just 2 rows of bolts here and 2 rows of bolts here and just made the connection longer. So had the same number of bolts, but basically had longer rows. So then I would only have 60 millimeters as my D, which would cut that value of 2.4 in half, and then certainly I'm going to be okay. Okay, so now that we have our connection design, I think I've convinced myself that shrinkage is going to be reasonable. Let's do all of our strength criteria checks and see if this connection satisfies our strength criteria. Okay, so I'm not going to go in extreme detail on this because we've covered it before in other examples and in the description. So yielding resistance, you know, as you know, we're going to get our G. This is for glulam, which I get from that table in the appendix. I calculate my embedment strength. I'm only looking at parallel to grain because I only have parallel to grain loads here. So I calculate my Fi theta as just my FIP times KD KSF KT, since my theta is equal to 0. And I get my embedment strength for the wood members, which are the side members, and that's F1. F2 is steel, so I'm going to use this equation. Okay, I've already said that this is A36 steel, so based on that, I can pick my phi steel, phi y KSP, and FU, and those numbers are given in the standard, I believe, for A36 steel, which is what I specified, and I get my F2 as 1200. Then I get my bolt strength for A307, which is there. My T1 is my side plate thickness, which I have already calculated. Okay, that's just one side of the plate, the thickness of one side of the plate, and T2 is the thickness of the steel plate, which is the element in the middle. So I go through, I calculate all of my Johansen yield equations for a 3-member connection, and I find out which one is the minimum one, and it turns out to be the D failure mode in this case. which is not nail yielding. This is bolt yielding in the side members. Okay, and so that's good. So basically this is a ductile failure mode that would govern. I mean, all of the Johansson yield equations are moderately ductile failure modes, but this one is based on bolt yielding. So that's pretty good. That's probably because we're using the 3/4 inch bolt. That's very long. I'm assuming that I can procure this bolt. Okay, that's something that you need to check in practice, that you can actually get that size and length of bolt. Okay, and then for overall, so that's my per bolt strength. So then now I can calculate my total strength. I have 2 shear planes because I have a 3-member connection. I have 36 fasteners, 6x6 in my setup, in my design, and then I get that my total resistance is 1227 kilonewtons, which is greater than my design, right? Remember, my design strength is 1109. So if I go all the way to where I calculated the first time, right, my design strength was 1109 kilonewtons. So I'm above that by a pretty good margin. Okay, so that's my yielding strength. So that's one failure mode. So now I'm going to look at the brittle parallel to grain failure modes: row shear, group tear out, and net tension. Okay, so starting with the row shear, I get my strength. That's my shear strength from the table, 2.0. So as I mentioned, like most of the glulam members have 2.0 as the shear strength. Our wood members here are side members. So I'm just looking at the wood member shear strength here. Obviously, the steel member row shear strength I have to calculate using S16, which we're not covering here. So I'm just looking at row shear strength of the side members, which are the wood members. So since they're side members, my KLS is 0.65. My thickness I already had. I have 3 fasteners in a row. And my ACRI, as we mentioned before, is the minimum of AL, the loaded end distance, or SR/SP in 08619, which is the within row spacing, the spacing between bolts in a row. So that's why, remember, I made my AL 120, because if I made my AL any less than 120, then my ACRI is going to be less than 120, and I'm going to lose a lot of strength in my connection for basically no reason, other than me making a poor design decision. So I calculate my spacing of one row, or my strength of one row of bolts. Okay, these are all 1. My KLS I just found, my T I know, my NC is 6, my ACRI is 120, and I get 145 kilonewtons per row. Then I have to find the minimum shear resistance of any row. All of my rows are identical, so this is equal to just that single row strength. Then I need to find the total factored shear resistance for member 1. So remember, I have 2 members here because I have my knife plate. Actually, I have 2 knife plates now. So I have a situation that looks like this. If I look at the cross section of my member, this is maybe the worst drawing I've done yet. Okay, these are steel plates in the middle here. And so I have member, this one is one side member, this is another side member. So in the row shear calculations from the standard, so for my row shear calculations from the standard, I look at these as separate members, right? In the table, both of those were considered together. You know, since that table was specifically for this condition where I have 3 members and rows on both sides. So this is for just a single member, so on one side, and I get 611. Now, both of those side members have the same strength, so this is the one for member 2. So here I have PRR1 and here I have PRR2. And then to calculate the total factored row shear resistance of all the wood members on that side of the connection, right? I'm talking about the wood side of the connection. I add those together, I get 1222. This is almost exactly the same as the yielding resistance that I just calculated, and that's not an accident, because remember that when I calculated this using the table, I had the spacing 120 was the spacing at which row shear no longer governs, and yielding governs instead. So at 120 spacing, Let me remind you exactly what we're talking about here. Okay, so when we are on this page here, remember we had two values for spacing parallel to grain. We had the 76 or we had the 120, right? And why is this greater than or equal to 120? Because if I go greater than 120, then row shear doesn't govern, yielding governs instead. So 120 is kind of my maximum effective row shear length. Any greater than that, and basically row shear is not governing anymore. I mean, which is good. We don't really want row shear to govern if we can avoid it. It would be much better for yielding to govern. But anyway, so that's why this is the demarcation point between row shear governing and yielding governing. So when I do that calculation, it's no mistake that I find that this is the balance point between row shear governing and yielding governing. Like they have basically the same strength here. Okay, so that makes sense. Okay, so now let's do the group tear out resistance part. Okay, so for group tear out, we have two different groups, and I've drawn the geometry here, and we're going to get into a little bit of trouble because when I did my assumptions, I assumed a certain row shear, I assumed a certain width of that tension leg, and you know, I said, okay, I'm going to assume that I'm going to have basically greater than that. But now that I've spaced these things out according to minimize my shrinkage, I've actually probably undershot that. So let's see what happens. So these are my two groups that are going to tear out, right? Like this part is going to basically tear out the back here when this, if this connection fails in a group tear out. Okay, and same for the other one. And they both have to tear out in order for this connection to fail. Okay, so that's the geometry. Let's do the calculation. So the row shear part I've already calculated from when I did row shear. The first row and the last row have the same. So basically I'm looking at this top tear out condition. Okay. So the first and the last one are going to be the same, which is basically the same row shear resistance that we calculated when we did row shear. I need my tension strength for FTN from my table 7.3 for glulam, or 7.2 in 086-19, and remember my hole. So now I'm calculating my APGI. Okay, so here's my group tear out, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and in the middle, 1, 2, 3, 4, 5, 6. Okay, so I have to calculate basically what is the net area on this portion here, the orange portion. Okay, so 120 is the total distance between the centers of the holes, and then I have to remove two half holes and one whole hole, if that makes sense. Okay, there's a half hole here and a half hole here because that dimension 120 is between the centers of the holes, and then in the middle I have one full hole that I have to remove. And then I multiply that length that has removed the bolt holes times the thickness of the piece, okay, which is just my 130 here, and I get 10,088. Okay, now I use this equation to calculate the group tear out resistance. We have to remember that these values, I need to input them in newtons if I'm doing this by hand, because otherwise it will not be the same unit as this side of the equation, which is going to come out in newtons if I do MPa for this and millimeters squared per this. Okay, so when I do that, and here I have a factor of 2. Why? This is not part of the equation. It's because here in my group, in my situation, have a pretty weird situation where I have two groups that are tearing out simultaneously. I'm not looking at this group tear out condition. I mean, I could look at that one too, but that one is not likely to govern at all because that area in tension is going to be so high that we'll basically never tear it out. So I'm looking at kind of I'm looking basically at these as two separate connections that are having group tear out. And I think this would be, you know, the right approach here. As we'll see by finding that the resistance is going to be lower than my shear resistance. If I do this total group tear out with the orange line, then group tear out's not going to govern for this connection. So I have to make sure to check this one in this case. Okay, so I check this and I find that for each wood member, again, I'm doing R1 and R2 on either side of the steel plate, I get 492 for each. And so adding those up so that I get the full group tear out resistance for all members on that side of the connection, I get 984 kilonewtons, which is lower than my design strength. Okay, so that's kind of bad. Okay, so it turns out that assumption I made at the beginning that my groups are going to be wide enough. I mean, you know, I've prepared this ahead of time, so I've left this kind of error in here as an example of you know, making a bad assumption. Okay, and that's not necessarily a big deal. I've made kind of an awkward assumption here that didn't turn out to pan out. You know, not all the assumptions I make are going to be true when I'm going through my design process. That's why I'm checking at the end to make sure that everything makes sense. So, you know, once I split these bolt groups into two, I basically have reduced my total group tear out, because now I'm considering them as two separate groups that need to tear out. And I'm using the minimum row spacing because I want these to be compact so that I don't have a shrinkage problem. Okay, like before, we were assuming that I just had one big group of bolts and all of the 6 rows were going to be together. But now that I have considered shrinkage and modified my design to minimize shrinkage, now I have a group tear out problem. Okay, so I need to solve this problem. What can I do? I could make the rows further apart in order to make that tension area greater. I wouldn't have to go too far because you can see I'm pretty close here. I'm within about 150 kilonewtons. But I don't really want to do that because it's going to aggravate the potential shrinkage problem. So instead so that would increase this term, right? So if I increase APGI by separating the rows a bit more, that's one way to increase this strength. The other way to increase this strength is to increase the length of the rows. So I'm going to increase my row shear resistance as well, which is fine. And in the process, I'm going to increase my group tear out resistance, which is what I need to do. Okay, so how much will I have to increase my strength? I need about another 63 kilonewtons of strength on each side of the connection. Okay, that's basically this distance here, this distance divided by 2. That's how much extra row shear strength I need on each side of the connection. Like, for not each side, each member, basically each member in the connection. Okay, so I'm trying to figure out how much I need to increase this. I could do a trial and error approach to do this. But basically what I'm going to do here is try to figure out exactly how much I could increase this by. So this is only the first half of this equation. Okay, so it's basically just this part right here. Okay, I'm finding out what is the current strength of that part because I know that I have to increase it by about 62.9 per side. Okay, so if I just do that first term, I get 203. So I have to increase it by 62.9 per side per member. So I have to increase it then, it turns out, by approximately 30%. And shear plane strength is about linearly proportional to the row spacing, right? As I increase my row spacing, I increase my shear plane strength. So I increase my row shear strength accordingly. So I'm just going to increase my spacing, which was previously 120. That's this SR or SP, and it equals 120 right now. I'm going to increase it by about 30%, and that should do the trick. So I increase it by 30%, I get 157. I'm going to round that to 160. So I have now revised my drawing. I've made my connection a bit longer. Okay, this is longer than what I assumed it was going to be at the beginning. Remember, I thought it was going to be around 700 millimeters. Now I've increased it to almost a meter long. Okay, I would have had this same problem with any of the different connections that I would have done for group tear out. So yeah, so now I have my revised drawing. So I basically only changed these spacings. So I changed this spacing, and I also had to change my AL, because if my AL is less, then I don't get any benefit from increasing the spacing between the bolts. Okay, so yeah, you can see now my length is about 960, the length of the bolts themselves, if I don't include the steel plate behind. Okay, so the yielding resistance is not going to change because the yielding resistance has no effect On the spacing of the bolts, it only is affected by basically the geometry of the bolts and the thicknesses of the members and the embedment strengths, none of which are going to change. So yielding is still going to be fine. So I don't have to recheck that one. I've only changed AL and SR, which I just mentioned. So now I'm going to check my revised row shear resistance, which is the exact same calculation that I did before, except with a different ACRI has changed now. It's gone up about 30%. So my strength has also gone up about 30%. So my overall row shear strength has gone up by about 30%. Okay, so I get 1629 for my row shear strength. Now I'm going to check my revised group tear out resistance, which I'm pretty sure is going to govern, is going to be fine because I just revised my design according to group tear out. I go through the exact same process that I did before, and I come up with a total group tear out strength of 1119, which is just barely bigger than my NF of 1109. So it looks like group tear out is going to govern in this connection. Now, is that a good connection? Yeah, it can be. It's not necessarily a problem. If I'm relying on ductility in this connection, then this would not be good. So if this was an earthquake design where I am relying on this connection to dissipate energy in an earthquake, then this would be a bad design. I would want to make sure, for sure, that yielding is going to govern in a connection like that. But there's no indication that that's the case here. I just have kind of a regular tension connection. I'm not assuming that there's any ductility in this connection. So basically I have a brittle failure mode. It is what it is. Okay, so I have 1119, which is greater than 1109 by about 10 kilonewtons, which is no accident because I basically designed it to be that way. I could design this to be greater by, again, increasing the rows further away, or maybe increasing the distance between the rows and, you know, taking the hit in shrinkage a little bit and relying on the dimensional stability of glulam. Maybe. Okay, the last check that we didn't do the first time because we didn't get that far is net tension resistance. Okay, so I'm basically using the clause 7.5.11 in glulam, which we learned way at the beginning of the course. To do my check, I calculate my gross area. I calculate my net area by subtracting the slot, and then by subtracting basically my bolt holes over here, over 6 rows of them. And I get this value for AN, and then I'm just double checking here at the end that I am less than 25% of material removed, which is my requirement for net tension. But of course, I chose 6 rows based on that at the beginning. Remember, this was an approach I took at the beginning. So you can see how important it is that I check that near the beginning, because I could have gone all the way down to this point and said, okay, well, I can fit 10 rows. Remember, the original thing was I could fit 10 rows of bolts according to the spacing requirements, and then come down here and calculated my net tension and saw, oh, geez, but you know, I'm taking out too much material. I've taken out more than 25% of the material, so my entire design is no good anymore. I have to go back and redesign everything. So it's good to do all of those checks at the beginning, of course, when I'm trying to lay out my geometry in the first place. So don't forget that 75% net area requirement. Okay, so I do my FTN and my FTG. Since I'm doing glulam here, I have 2 checks. I check my FTN strength. I get 2291, and I check my FTG strength, and FTG governs, as it almost always does. I see that that's much greater than my TF. And that's obvious as well, because we determined what our applied load was as to be approximately half of my gross area, my gross strength. Right, so that makes sense. I mean, I'm just doing this check for completeness, basically, because I never checked the net area. I only checked the gross before. Okay, so now I've done the yielding check, I've done row shear, group tear out, and net tension, which are my parallel to grain checks. I don't have any perpendicular to grain force, so I don't have any splitting check. And since I only have load in the parallel to grain direction, I don't have to do the interaction check between parallel and perpendicular. So when I check my overall requirements for the connection at the very end, my QF is 0, because as I said, I don't have any perpendicular to grain force. My PF is equal to my NF. So if NF is my total force, all of it is parallel to grain. Therefore, I need to check my total requirement for yielding and my total requirement for parallel to grain loading. and C and D, which are the perpendicular to grain, and the interaction between parallel and perpendicular, I don't have to consider. So here, I'm just laying this all out and making it super clear that I satisfy all the requirements, even though I already know that I satisfy them all. These final checks are most important when I have loads in both the parallel and perpendicular directions, because in this case, once I've gotten to this point, I already know that my NF is greater than my PR because I checked it at every step. But if I had a perpendicular to grain component as well, I won't know until this final point whether the interaction equation is satisfied. So that's why I include this anyway. So yeah, my NF has to be less than or equal to PR, because this is a PF equals NF, right? It has to be less than PR, and PR is a lesser of row shear, group tear out, and net tension, and group tear out's the one that governs, as we already discussed. And so I have to make sure that my NF is greater than, is less than my applied load is less than my PR of 1119, which is fine. So therefore, my revised connection geometry presented in the revised connection geometry drawing is adequate to resist 50% of the total member resistance and tension. And I've drawn that connection out already, so I haven't repeated it here because I already have a total detailed design drawing. So this is my final connection design right here in a nice overall drawing. And that brings us to the end of this connection design example. So you see that more than half of the effort that we put into this example was just in laying out the bolts and figuring out what would be the reasonable layout. And we also had to spend some time in iteration because we saw that one of the assumptions that we made at the beginning of the process didn't actually pan out. So we actually had to repeat some of the work. And, you know, c'est la vie. That's the process of design, is that we are going to often have to go through some iterations. We had iterations at the beginning, we had iterations at the end. It's never really a clean process when we're talking about engineering design, but luckily it is a fun process. So I hope that you enjoyed this kind of epic bolted connection design example, and it'll help you in projects and work in the future. And that is the last bolted connection design example.